A problem or loading scenario is deemed statically indeterminate if the equations of equilibrium are not sufficient to determine all of the unknown loads or reactions on the member. In other words, there are more unknowns than there are equilibrium equations. Consider the member shown below, which is fixed supported at A and B and subjected to an axial force of 500 newtons at point C, with a constant cross-sectional area A and elastic modulus E. Since a fixed support, as we learned in statics, prevents translation and rotation of the member at the point of connection, then we have, in general, three support reactions at each end: horizontal and vertical force reactions and couple moment reactions at both A and B. Since the axial load at C acts vertically along the centroidal axis of the cross-section of AB, and there are no other applied forces or moments, then the horizontal reaction forces and couple moment reactions are zero and can be eliminated or neglected from the free body diagram. So here was that original free body diagram we showed just a second ago, and here's the simplified free body diagram showing only the reaction forces in the vertical directions at points A and B that we're now going to call F sub A and F sub B. The only equation of equilibrium that is of value in this case is equilibrium of forces in the vertical direction. We have F sub B plus F sub A minus 500 newtons equals 0. Now we're assuming, going into this, directions of F sub A and F sub B, but we do know they have to act vertically. Since there are two unknowns in the above equilibrium equation, this equation is not sufficient to solve for both the unknowns F sub A and F sub B. Therefore, we see that this problem is a statically indeterminate loading scenario, and we need an additional equation that relates F sub A and F sub B. An equation that specifies conditions for displacement is referred to as a compatibility equation or kinematic condition. Here, the axial displacement of A relative to B must be 0, since A and B are fixed supports and thus no relative movement can occur between them. Delta sub AB relative axial displacement A to B must equal 0, as we stated, because points A and B cannot move. And we know from earlier part of chapter 4 that total axial displacement of this segmented member would be the summation of two different axial displacements, delta sub AC plus delta sub CB. Delta sub AC is the axial displacement of A relative to C, and delta sub CB is the axial displacement of C relative to B, and we can further equate that delta value in each case to NL over AE for that segment. And remember that A and E are constant throughout this entire member. Consider the free body diagram of each segment upon applying the method of sections between A and C in segment AC, and between C and B in segment CB. Okay, this here shows the internal axial or normal force in this segment AC. This here shows the internal axial or normal force in this segment CB. So we see that the internal axial force in segment AC is F sub A, that's equal to the magnitude F sub A, causing tension or elongation of that segment because F sub A goes away from the member. And the internal axial force in CB is F sub B, causing compression or contraction of that segment because this force here, the internal force there, is into the member. So applying the sign convention for axial loads that we mentioned earlier, we have the following. N sub AC is positive F sub A, and N sub CB is negative F sub B. Noting that L sub AC equals the length of segment AC that was given as 2 meters, and L sub CB equals the length of segment CB that was given as 3 meters, and that A and E are constant, the compatibility equation becomes the following. F sub A times 2 meters over AE minus F sub B times 3 meters over AE must equal 0. Solving the equilibrium equation in conjunction with this compatibility equation, we obtain F sub A equals 300 Newton and F sub B equals 200 Newton. This example has demonstrated how to approach solutions to these statically indeterminate axial loading problems.